going to keep talking about hypothesis testing. We'll look at methods for proportion. Right? It's following a lot the same logic as before. By proportion, you get a different formula for the standard error. Things look a little bit different. We'll also talk a little bit more about power, or the probability you reject the null hypothesis. But it is in fact false and should be rejected. What affects power a little bit. But any questions before we get going? The homework due is due on Friday. I think after this class you have most of what you need to do it, or at least substantial parts of it. Right? And then Wednesday we'll look at some more examples. We'll kind of refine that interpretation of confidence intervals and hypothesis tests, kind of the connections there a little bit more. So for proportion, we have the kind of the same situation, that there's some population that we're interested in, and there's some proportion that describes the rate of having some characteristic or some group in there that's and we're going to have some sample data, and out of that we're going to record the number in the sample with the characteristic, or in a particular group or something. And we had a sample size of n that to ask a question to classify them or see what results, do they get better or not. And so we're going to get a sample proportion as an estimate. B hat is going to be x over n. And we want to go this way to do inference for our population value p, right? And hypothesis testing, we set up a hypothesis about that population proportion, and we're going to see if the data are consistent with that or not. So we're going to set up a null hypothesis that p equals some particular value. That we're interested in. Again, null hypothesis usually means no effect, no difference. So if there was a standard therapy and at a certain success rate, you might ask, the null hypothesis means that the new way of doing it is the same success rate. Or maybe we had the rate from the time before, and we know that really well, and now we're into a new period and seeing if things have changed. Right? Every once in a while, there's a certain percentage of adults that smoke, and then you come in and change the tax laws or enforcement or something like that, or do a media campaign, and you ask, is it still the same after all that change? So the null hypothesis is, no, it stayed the same. It's just that old value versus an alternative. And this can be, is not equal to that value. In some cases, we'll have it that it's less than, where we really are interested in, does it make it less? Like if all these things that we're doing really are intended to decrease the smoking rates by putting more tax, more anti-smoking education, more enforcement of laws about who can buy and all that stuff, then you would think it'd be less, and you might clearly have an idea that it's supposed to be less and make your alternative one-sided. But the idea is if p hat is close to p sub 0, we're not going to throw it away. It's not going to exactly be p0 in a random sample, but it might not be too far away. If it's far enough away, we'll go with the alternative as more and more reasonable. Right? But the question is, how do you measure distance? Right? Is p0 is 0.5 and you get 0.6, is that too far away? Or is 0.55 too far away? It's all going to depend on the sampling distribution and the standard error. So how far does p hat need to be away from p sub 0 for us reject the null hypothesis that said that P is equal to P0. So we have some number line here, and here's our P0. Our null hypothesis value says it's there, but we've got a P hat down here. And is it far away? Is there sufficient evidence? Well, we're going to look at the sampling distribution of P hat under the null hypothesis. There's a few things that we know about the binomial experiment. In a binomial experiment, that if X is distributed as a binomial, that we're taking a random sample, asking n individuals a question, and then it's yes or no answers, and they're independent as binomial. For probability theory, the expected number who say yes or fall into that category is n times p. The variance of X is n times p times 1 minus p. And if n is large, n times p times 1 minus p greater than 10 certainly works. Sometimes they say greater than 5, or break it up, n times p greater than 10, n times 1 minus p greater than 10. But so anyway, n reasonably large. Then X is approximately normally distributed at the mean for that, and at a variance in p 1 minus p. This was an example of a central limit theorem, CLT, that gives that distribution. So that's like a sampling distribution. The sampling distribution exactly is binomial, but it's approximately normal. P hat, our sample proportion, is that X over n. So in probability theory, right, the expected value of P hat is just going to be this mean divided by n, so it's whatever p is. Right, so this is our sample statistic. Equals the population value. And the variance of p hat, well, when you divide by n, right, divide by n here, you get an n squared in the bottom of that one. So the variance of p hat is p times 1 minus p over n. And if X is approximately normal, it turns out that p hat also is approximately normal. But in our hypothesis testing, we know even a little bit more. This is kind of just reviewing probability theory from that section when we talked about that. We kind of reviewed this a little bit with confidence intervals as well for proportion, right? But it's kind of this underlying theory that's there. But if the null hypothesis says that p is p0, right? If that's true, right, then this thing's p0, and this is, we know what this is too, right? So under the null hypothesis, we know even more. Right? If the null hypothesis is true and p is actually p0, p hat is approximately distributed. Again, there's this normal approximation to the discrete thing here, but it's centered at p0, and its variance p minus 1 minus p0 over n is also known, and that's a variance. And if we have p0 here and a value of p hat, we can ask the question, well, what is unusual? If the sampling distribution is kind of centered here at p0, what's unusual? A standard normal, if we are looking at 5% 0.05 significance level. And we're looking at a standard normal and a variable. We find places under the standard normal that have the 95% of it. So we look at what is the tail. Two-sided, we put 2.5% in each one of these. And we know for a standard normal that cutoff value there is 1.96, almost 2 standard deviations, 1.96. And this is less than 1.96. So if our standardized value ends up out there, it's going to be unusual. The standardized value in this case, and we have our value of p hat, we subtract the mean, divide by the standard error, the square root of that. We get a z value. So if our standardized value ends up being greater than 1.96 or less than the negative of that, it's going to be an unusual z value. Yeah.
All right, so this is kind of, it's on topic but off topic at the same time.
Okay.
So should we try to memorize the negative 1.96 plus 1.96, or is that something that would be given to us in NEs?
Well, the 1.96 is for normals, is going to be just a standard value for 95%. So it would come up in a few contexts. We're going to kind of have a repeated of that value. The other thing is that I'm likely to give you the normal table, right? Like the standardized normal curve table that's in the back. So, you know, if you need to look up 97.5, you know, this is 2.5%, this is 95%. If you add those together, you get 0.975. That probability actually shows up right in the table at 1.96. Right. But usually for 5%, we're going to be close to 2. So even when we were dealing with means, the t-distribution, you know, 1.98, 2, kind of be in that ballpark. The t-distribution in means, you might look it up on the t-table, and you don't need to memorize those, because there's one for every degree of freedom.
Okay,
Yeah.
so another question, is PO for the
Null hypothesis value?
null hypothesis value? Okay,
Yep.
thank you.
Yep. Right. So if our z value is greater than 1.96, or the z is less than negative 1.96, we're going to reject null hypothesis and conclude that p sub 0 probably is not reasonable, right? And should not be kept as a plausible value. So let's look at one example. But any questions about that? Right? So kind of the probability theory gives us this distribution under the null hypothesis. And then if our p hat is unusual according to kind of a normal reference distribution, then we'll reject it. Right? So the percent of the population with college degrees, right, a newspaper, right, paper says 20%. Now you take a sample in a particular area. People in the survey, and in this particular survey, 16% report having college degrees. Is this area or this sample, is the people responding to this, is what the newspaper says as a 20% figure accurate for this group? population that this one represents. So what would be null hypothesis?
Quick question.
Yeah.
When the newspaper is saying 20% is, and the n is equal to 100, is that equal in the same area, or is that in?
Well, so that can
Or
be
is
kind
it-
of a, that's a little bit vague in terms of the description of the problem. So you could have, a 20% rate, that they say 20% of the people, maybe in the state of Vermont, or say they have college degrees, right? So somewhere that number's coming from. Something.
Okay.
Is that general knowledge? Is it what the Census Bureau says? Is it based on, something? Is it just kind of an approximation they made up by looking at something on Wikipedia? Who knows? Right. And then this is an actual sample in an area. Maybe it's a nationwide sample, but you can think of it as maybe being a sample of the adults that you can get in Vermont now. Maybe that 20% was a few years back.
So, I'm sorry to be trying to clarify the question here, but so the 16% then is, we're asking is significantly different than the 20%?
Yep.
Okay.
Yep. So, in terms of setting up null hypothesis.
It would be not.
Or not equal to, right? So we could have P equal to something versus P not equal to something.
So P is equal to 20%?
Yeah. So we make the null hypothesis about the kind of stated population characteristic. We wouldn't want to make a null hypothesis about the sample because that's only based on the data, it's not necessarily. So emphasizing writing down the hypotheses is you make the hypothesis about that. Would you reject this one? So we do the z-value, p hat minus p0, p0 minus p0, n. And so 0.16 minus 0.20, and then 0.20 goes down in here, over 100. And so this would actually just be -1 as a z-value. But a z-value of -1. Do a test at a 5% level, significant level. Right? We would reject if z is less than -1.96 or z is greater than 1.96. But -1, one standard deviation below the mean, that's not so unusual. It could happen by chance. It's not right at 20%, but it's kind of within the variability that would be kind of naturally occurring and not be so surprising. So based on this, based on z equals -1, do not reject the 20% figure. Okay? It's not sufficiently far away. What if instead, let's imagine that we got some other things and you can work through a couple numbers or at least write them down. But any questions on the conclusion? So we could imagine that we had 100 people. Right? P hat is 0.2, n equals 100. A different one, P hat equals 0.28. Or n equals, say, 400. P hat equals 0.16. In these cases, what would happen to our null hypothesis? I'm going to take a couple minutes to write down formulas for getting the z-value. These numbers work out conveniently, so you can figure out what the z-values are.
And the null hypothesis, okay, is still
Yep,
P's.
same null hypothesis. we're kind of imagining different scenarios to get different samples. What if it had turned out to be different? Any questions as we're going through it? What about the first one?
We don't reject it, it's the exact same as C.
So Z value is 0, right? Right at the exact spot, so don't reject. So the sampling distribution is centered at 0.20 for p hat, and we hit right here in the middle, right? And so the difference between p hat and p0 is nothing. So it's totally consistent. We don't reject. Right? So if you're really close, you don't reject. How about the second one?
Do you reject?
Z is equal to 2, right?
Well, -2.
Oh,
Oh, 2, sorry. I screwed it.
Yeah. P hat
screwed
minus
the sign,
P0, P0, 1 minus P0 over N. And so one thing to emphasize within this, that the P0 stays the same because the null hypothesis in this case tells us what that one is. In a confidence interval, we changed, right? The confidence interval, we would have changed this thing to 0.28. In a confidence interval, we're not starting out with a strong hypothesis like that. But anyway, it's 0.28 minus 0.20 and 0.20, 0.80 over 100, and it ends up being 2. So we end up rejecting no hypothesis, right? Because our Z that is 2 is a little bit bigger than the 1.96 value. How about the second one? What do you for that?
Except, because it's -1.
Except the -1,
No. It's,
the 400.
Oh.
it's
okay.
-2.
It's also, yeah, it's also getting -2 in there, right? So even though the difference, 0.16 before, the difference, right? Because you have a bigger sample size, the sampling distribution is narrower, so a difference of 0.4 with a small sample size is not significant. With a bigger sample size, because the sample distribution is narrower, you get a better peak. It's enough. If it was 0.16 based on 100, it's not quite enough. But if that continued, and you got up to 400 people, then that was enough, right? So 0.16 minus 0.20, right? And then 0.2, 0.8, and now 400 down here. Again, it's -2, so we would reject in that case as well. But any questions about? Yeah, do you have a question?
I think you said it before, so if it's less than 0, you reject it, right?
So if it's less than the negative 1.96, so going back to the normal, so a standard normal, so here at Z, if it's negative 1.96 to 1.96, if it's at these areas, right, we reject. We're doing two-sided because the alternative hypothesis in this simple case is just two-sided. So if there's 95% of the area in the middle here, if we get a result that is out in the left, outer 2.5%, cumulative, that's 5%. Right? Under the distribution of p hat, this thing is centered at p0, and then that's 1.96 times the standard error. So if it's out there, we reject it. Yeah.
Okay, so to be clear, what we're, with the, if it's less than 1.96, then we know that its p-value is less than 0.025, so when you double it, it would be less than point.
Yeah, so,
Okay,
so
that
there's
makes sense.
a chance of, another way of looking at it is quantifying this in terms of p-values. Right? So let's look at that as an example. So we can look at p-values. Right? So the p-value, again, like last time, is the probability of a result as extreme or more extreme, as extreme or more so than our observed value under H0, assuming H0 is true. So if here's distribution of p hat, it's kind of centered under here, under p0, and we actually get a value of p hat out here. We're going to calculate the tail area under the normal distribution with the mean and variance determined by the null hypothesis. Right? This is called a tail area probability. Tail area probability. And if our alternative is two-sided, we're going to double that and call it a p-value. If our alternative is one-sided in that direction, then we're just going to call the tail area the probability. And we won't worry about doubling it because we would have justified looking in one direction before ever doing the study and call that our probability. If that probability is small, that means we're out pretty far away. Right? So we would always reject for small p-values. So small p-value means that the null hypothesis and the data are far apart, right? And we reject. So let's do one example. Suppose that Rogaine helps about 40% of the men with hair loss. Has a 40% success rate. And there's a new treatment. That comes along, right? Dimethyl polysiloxane. It's actually, there was a news story about 6 months ago. That's a material. This is actually a product. It's a McDonald's French fry.
Oh, that's great.
It seems to stimulate different cells and growth. So it's either it's thinking about putting that on your head. It's something else, and also thinking about eating it. It's like
Eat more French fries.
eat more French fries. So
But specifically McDonald's French fries.
I guess so. Right. Preliminary testing. 227 volunteers with hair loss, and 130 show improvement. This would be a p hat 130 over 270 is 0.431, so a little bit less than that.
And so we're just testing just the new treatment, we're not doing the control versus the new treatment, right?
True,
Okay.
right. Yeah. So in some settings, it would be better to get a group of men and randomize them to treatment versus, standard therapy, Rogaine versus this new one, with the idea that then you're sure to get the same population. People that volunteer or sign up for this testing might be different than the general population. So, but hopefully these 270 are similar to the people that actually determined that, or otherwise there could be a bias. So, yeah. We will do a confidence intervals hypothesis for comparing two proportions. If you did randomize it to two, we'll get that. That just adds a little bit of complexity, but it's a lot of the same logic. Right? As that is. And does this new testing look better? This new product, new treatment of this look better? Does new treatment do better? What's a null hypothesis and what's an alternative? Which number do you want to use as the null value? 0.4, right? The one that's been determined a long time, kind of the standard, no change from that. This is a case where if we're trying to show that this thing's improvement for the purposes of marketing, and you kind of done some other preliminary testing, right? So where do they do preliminary testing? They probably do some testing in a petri dish, basic science, chemistry, biology, to see if it seems to have effect on cells. Maybe take a few volunteers, like phase 1 clinical trials might just take a few volunteers, like 5, to see if there's, if it causes major reactions, or is this kind of safe to use. Some other ones to see if it does any type of positive thing. They do some small scale volunteer studies to try to get dose right. Not too much, not too little, things like that. But at this point, they're kind of doing it, this preliminary testing, I guess we want to say, is it bigger? If it's not bigger and doesn't have any other advantages like cost savings or something, you're not going to be able to sell it. But if it has a better rate, you can sell it. So let's think of a Z statistic. Right, same formula, P hat minus P0, P0, 1 minus P0 over N. And so 0.431 minus 0.40, and we use the null value in the standard error because the null hypothesis tells us that's what it should be. So 0.40, 0.60, and there were 270 volunteers over square root. This is the Z value of what?
1.04.
1.04. So based on that, we're not going to reject. It's not far enough away. It does not seem to be sufficient improvement. P-value is going to be the probability that a standard normal 0, 1, right, is greater than that 1.04. And that probability is about 16%. The chance that you're bigger than one standard deviation under a normal is this is a standard normal. I think there's one extra. Oops. There's one extra line there. The chance that a Z is bigger than one that this is a standard normal. It's about 16%. So about 16% of the time, you're bigger than 1, right? And that's called the p-value in this case because we're looking at one side. So because the p-value is bigger than 5%, we reject. That's another way of phrasing the conclusion. Right? The p-value is greater than 0.05, so do not reject. This product does not look so much better than the standard.
you don't necessarily care which way go about like saying we do not reject or.
Yeah, so this kind of conveys the same information. I mean, if you have the z statistic of 1, that does it. People usually don't write the z statistic. I mean, it's just, they give you the test statistic in an article, but they might give you the p-value.
Because I remember like a couple classes ago, you said you always use the p-value.
Yeah, or communicate as much as possible. So I would want to know, you know, the 270 and the sample rate of 0.431, and in comparison to the 0.4 going a one-sided hypothesis. You know, it's a z-value that or p-value that. So the more you communicate, the clearer it is. But if you just give the p-value, and I know that kind of basic information, what type of test you're probably doing, then I get an idea of what you've done. Yeah.
So, with this, I understand this wasn't the original question, but wouldn't this also answer the question of whether it is as an effective treatment as because we've shown that there's no significant difference between it versus Rogaine?
Right. So this one is this one that does it do better? So it's asking, is the proportion actually higher? It certainly is higher than 0.4. So, you know, if you phrased it as, if this is kind of a generic brand or alternative that's going to be sold for cheaper, you might want to say not necessarily that it does better, but that it doesn't do it any worse. Right? And so, does the new treatment not do worse? Well, it actually is better. So the sample proportion was better. So that's encouraging. But if you set it up that p is 0.4 versus an alternative that p is less than 0.4, right, you could look at it that way. Right? The z-value 0.431 minus 0.4 over the standard error is going to be the same thing, right, 1.04. But because this thing is looking the other way, so to answer her question, 1.04, because this one is looking to the left, we would, you know, really look that way. Instead of getting the p-value of 16%, you know, the p-value looking the other way is 84%, which clearly is not less than 0.05 when we would not reject. So depending on how it's phrased, and both things are done in medical testing, right? Usually you have to show something superior to get it marketed. But then there's testing to show that there's no side effects and things, or that it's not worse. So you kind of look this other way, hope that you don't reject because you don't want to have bad things happening. Or you're developing generics, right? You can show that something is not is at least equivalent or not much worse than that. You might actually get a number that's a little bit less than 0.4, but if it's not significantly less than 0.4, you might still be able to claim it's equivalent, or it might be equivalent. Right? So yeah, depending on how the alternative is, it depends on which way you go. In this case, with 0.431, you've totally failed to show that the alternative is better. Until you get a p-value over 0.5. Right. So the next concept is that we'll look at really is power and sample size.
Can you say that last sentence one more time? So because we did not reject the null hypothesis, the treatment was not better.
In this case, we do not reject the null.
Yeah.
Right? And the alternative was that it's worse.
Okay.
So we failed to reject the null. So we have not proven that it's worse. Okay. In this case, because that's the way we set up the hypothesis. So we do not reject the null hypothesis. No. We cannot conclude the new treatment is worse. So if we can even rework that example just a little bit. I'll do this right after we do that. So we had the null hypothesis that it was 0.4, and the alternative is, p is less than 0.4, and our p hat had been like 0.39, oops, 0.39, based on 270. Well, p hat is less than 0.4, so at kind of a first pass, that's not, it might be a little bit less, but is it significantly less? Our z value here would be the 0.39 minus 0.40, and then 0.40, 0.60, 270. And that's going to be a slightly negative z value, but it's not going to be very big. I don't know what it is exactly. So if the difference is 0.01, and then we do square root of 0.4 times 0.6 over 270 in there, but it was negative. So negative 0.34, the chance that a normal is less than negative 0.34 is about 0.37. So the z value is negative 0.34. And the p-value, the probability that a standard normal variable is less than or equal to negative 0.34 was about 0.37. So again, even though p hat's a little bit less, we can't say that it's statistically significantly less because it's pretty close, and our sample size kind of limits how much of a difference we can actually detect. This would be more kind of typical. Hitting 0.3 above, clearly you can't see that it's less. Anyway, it works out. Okay, power and sample size. So in doing tests and in planning things, right, we usually choose alpha, our significance level. Is the probability of a type 1 error, and the probability we reject if the null hypothesis is true. Sampling distribution of p hat, so distributions of p hat. Based on alpha, we reject out here, two-sided alternative, we reject out here the tails. And so this little shaded area out here is our rejection region. That's where we reject the null hypothesis. So we usually choose that to be something like 0.05 because we don't want to make that error very often. It's kind of a standard, 0.05, 0.01, something small like that. But if the alternative is true, we want a pretty good chance of saying that that we rejected all hypothesis, right? If that treatment really was better, right? We want to prove it, right? So we want a significant result. So that depends on where the alternative is. So let's say, that p sub a is really here. And under the null hypothesis that it's not p sub 0, it's really there. Right? So we have a null hypothesis that p equals p0, and we have an alternative that p does not equal p0. Right? And in fact, under our alternative, we can get p sub a. Some specific value. Maybe we think that this thing is not 0.4, but it's really 0.45. Like preliminary testing can kind of suggest that that's what it's going to be, right? And so if it's really out here, the sampling distribution is no longer centered at p0, but it's centered over here. Right? And so power is the probability that we reject, that we're in the rejection region, given that the alternative is true. So under the alternative, right, there's just a tiny little sliver down here. It's usually really determined by one side. And the area under the red curve there to the right, oh sorry, that's not the right hand, it's in the rejection region. So right here, on top of that black rejection region there, right on top of that rejection region. So power is the probability that we reject H0 if the alternative is true. And so it's going to be the area under that alternative curve. And generally, if you're going to plan a study, we're going to want that to be pretty high. You don't want to go on something with a 20% chance of success. Right? That wouldn't be very good odds of proving your result, right? But having a power of 80% or 90% or at least 70% would give you a pretty, a much better chance of proving your result and being able to claim that your result is significant and therefore people should buy your product or do whatever. Right? So let's look at a numerical example. So let's say that there's a null hypothesis. Let's see, what did I do? Okay, that's just another thing. That, let's go back to one of my other examples we didn't do. All right. Well, keep working with one of these other ones, and so another treatment mentioned in the discussion of balding skewers growing hair is Nutrafol, and it has a success rate of 35%. Now let's say we're going to do 300 individuals. When do you reject? And let's do two-sided for now. When do you reject?
Are we still going off of the 40% from earlier?
We're going to say that this new product has a success rate of 35%.
Okay. So that's our H0.
That's the H.
Okay.
Right. So in comparison to this one, right, when do you reject? How much better does the new treatment have to be before you reject it? We're going to reject H0 if P hat, right, is greater than 0.35 plus. Now, what we're going to do is at alpha equals 0.05 level, so we get a 1.96 here. And then 0.35, 0.65 over 300. We're going to reject then, or if P hat is less than 0.35 minus 1.96, 0.35, 0.65 over 300. Get our couple of our cut points there. Let's see if I can make this, keep it up there a little bit for you. So if you want to keep looking at that, if I make this one smaller, I can put them both up there kind of. So 0.35 plus 1.96 times the square root of 0.35 times 65 over 300. We'll reject if it's above 0.4, or we would, doing a two-sided thing, reject if it's below 0.296. 0.404, 0.296. I can see it, right? 0.404 was 0.296, right? But let's say that this thing is so that would be the rejection region, above that or below that, if our p hat happens to fall on those, right? But now let's say this thing is better. The alternative, H0, P is 0.35, Hj, P is not equal to 0.35. Suppose P is actually 0.42. So it actually really is better than that amount, right? What is the power? Of this test? Remember we showed before alpha equals 0.05. So the power is going to be the probability that p hat is greater than 0.404 plus the probability that p hat is less than 0.296. We chose those two numbers, right, because there's 0.404, 0.296 there. If it's greater than that, we reject. If it's less than that, we reject. So up to that point, the alternative specific value doesn't work. Yes?
So for how do you find the 0.44 and 0.296? Is that different from like what we did before in the other example?
No, not really. Right.
No, so it's the same thing.
Yeah.
Okay.
So because it's two-sided, we're using the 1.96, and then there's a standard error and a standard error, and that's determined by the null value, the 0.35. So yeah, that would be the same type of determining the cutoffs. But now under the alternative, specifying the alternative, that is 0.42, we can calculate these probabilities, right? Because under this alternative, we should have a normal with mean of 0.42, and 0.42, 1 minus that is 0.58 over 300 is the variance. So we can standardize these two things and calculate the normal areas. What's the probability we'd be out in one of those rejection regions if the null hypothesis is true?
That's 0.5?
It's 0.58.
Eight, okay.
1 minus that. So that's it, if it's 0.42, we subtract 0.42 here. And we put the square root of that variance in there, 0.42, 0.58 over 300. And then we do that for the other tail. 0.296 minus 0.296. 0.42 and 0.4258 over 300. We are z values. Let me see if I can do this again. So 0.404 minus 0.42 divided by square root of 0.42 times 0.58.
Is the second one supposed to be p hat, or is it supposed to be 7? Or z, rather?
Oh, z, yeah. That would be a z. I'll fix that. And the other standardized one is negative 4.39. So this should be z, thank you. And that's the probability that z is greater than negative 0.56 plus the probability that z is less than negative 4.35. Usually one of these tails is almost 0, right, because it's in the wrong direction, right? From what you're kind of saying the alternative is. Right? You really expect it to be big, being lower is always kind of like a tiny probability. Right? But the chance that a normal is greater than 0.56, well, the chance that it's less than 0.56 is that 1 minus that, so it would be the chance that it's bigger, and that is about 70%. 0.71. this probability here is about 0.71, and that other probability over there is basically 0 for power, and this is about 71%. Not bad.
What exactly does the power tell you, though?
So the power, right, is the probability you reject the null hypothesis given a specific alternative reality. If the alternative is true, at the value you think it is, right, you really think that this thing is going to give us a 42% success rate instead of the current 35. What's the chance to actually reject if it's that, right? Because you could get, even if 40.42 is true, you could get a value that's kind of low, right? It's closer back toward 0.35. So there's a chance you won't be able to prove it. You'll get a p-hat that doesn't fall in the right entry region, falls closer to 0.35. But there's about a 70% chance you will get something out in the tails. Right? So it's kind of your chance of rejecting. Right? So power is also called 1 minus beta, where beta is the probability of a type 2 error. Right? Alpha was the probability of a type 1 error. And so this is the probability you do not reject if H0 is false. HA as your specified value is true. Another way of saying do not reject means that our p-hat does not fall in the rejection region. It falls close to p0. And so that's in the lingo of hypothesis testing. Significance level alpha, beta error that's often translated into 1 minus that, or power, the chance that you actually do reject. So when you plan, you want to get big enough sample sizes to have a good chance of rejecting. Right? So one thing that this comes up in is in pictures. Right? So let's say here's P0. This picture, your little tail down here, gives us the rejection regions. And if the alternative, if your benefit really is quite small, right, if piece of A is here, then the sampling distribution is this other picture, and the chance you're in your rejection regions, right, this should be a little bit smaller, I guess. Right, a little smaller tail out here than the rejection region probability. And all of this, this picture would have power is not good. It looks pretty small. Right? So you probably wouldn't want to go into this study and do it and pay for it. Right? Because your chance, if you're relying on getting a significant result to be able to publish your study or prove your product is better or something, then you don't have much of a chance to do it. Right? The chance you're in the rejection region, even if that alternative is true, is pretty small. It's not very good to do. Right? If, on the other hand, right, what would make power bigger? What makes power bigger? Generally, bigger sample size makes those sampling distributions smaller. Right? So I'll try to draw this in a different way. So instead of being maybe a very large sample size, and if this was a sampling distribution, so that you're going to reject for anything kind of here or here, right? A bigger sample size will make that sampling distribution narrower. The p-hat doesn't actually have to be so far away to reject. Then the piece of A distribution, it's narrow like that too, right? And you're going to have a pretty big probability under that curve with a bigger sample size. The other primary thing that would affect power is if a piece of A was actually further away. If this was actually out here more, you get more power. The chance of being this big or bigger increases as you move this curve out of the way. And as the difference between p sub 0 and this piece of A increases. So as you get a bigger difference between the null and the alternative, it's easier to detect. Right? It's massively different. You don't need a big sample size. If it's a small difference, you need a pretty big sample size. You can turn these into sample size formulas. Maybe we'll look at that on Wednesday because we're kind of running out of time to go through a more complicated formula. But there's a way to figure out how much of a sample size you need to make these curves narrow or small to get an 80% or 90% power if you want a reversal difference. All right.
What does the last bit say? And and S.
That's the difference in big.
Professor, here's homework. That would be, I have a few questions on it.
Okay.
I might ask tomorrow because it's been a really rough morning and
Okay.
like they
Sure.
dropped the class very late and so we're kind of going through.
Okay.
But I did get that done and I have half the other one done.
Yeah,
Good, thank you.
And then also I'm not going to be here on Saturday because I have to leave the office campus on that day.
Oh,
So
right.
I'm gonna try to get someone to you by Wednesday or
Okay.
Thursday rather.
All right, sure.
That's my.
Great.
Okay, thank you, Professor.
Shelley.
I was there for like 4
Yeah.
hours. It doesn't go over much. Thank you.
Yep. Thanks again.
Hello.
Hi, Martha. How are you doing?
Good, how are you?
Good.